All right, so let's look at example number 4. Freddy Physics shoots a hockey puck of mass 0.25 kilograms to the right at a speed of 38.1 meters per second. If the puck hits the boards so that a stopping force of 900 newtons brings it to rest, calculate the stopping time, or the time to bring the puck to rest. So this is a forces problem. So whenever you have a forces problem, you're always going to use the 5 steps for success. So before we do it together, go ahead and hit pause here and try to go back and do steps 1, 2, 3, 4, and 5 and see how far you can take this one. And then when you're ready, hit play and we'll work it through. All right, so step number 1, so I'll keep my little tally down here. Step number 1 says draw your FBD. So if we look here, you might notice this looks a lot like the problems we did last time where we had a box sliding across a floor. And I'm not the best artist, for example. So a lot of these things, like whether it's a hockey puck or a car or a box, it's always just going to be a box because the physics is kind of the same. So I'm going to do my little point mass there. I'm going to say the force in physics that always acts down is W, or the force from gravity, what we call the weight. Since this is a flat surface, our normal force will be going up. So the hockey puck, even though it's on ice, this time it still has that contact or support force going up. And then now, this hockey puck is sliding along. And I'm just going to say it was shot to the right, it says. So picture this hockey puck is sliding along to the right. And it's cruising along. And notice it's an object in motion. It wants to stay in motion. So notice this is the phase of the problem where it's just sliding to the right. And there's no force needed to keep it going to the right, because it's just an object in motion. It's going to stay in motion until an outside force acts on it. Well, in this case, the outside force that's going to act on it is the boards. So the hockey puck's going to slide into the wall, basically. And then since the hockey puck was going to the right, we know that the force that stops it is going to be going to the left. So in our picture, I just called it F stop because it's some stopping force from the boards. It's on a hockey rink, so they didn't say it explicitly, but we're going to assume it's basically frictionless. So that's step 1. We'll put a check right there. Step number 2, if we go back to our step number 2 here, all the way back to the front page of our packet, it says pick a coordinate system based on which way the object wants to move. Well, this object wants to move to the right. So again, our coordinate system is going to be just what our coordinate system is in math class. So we'll say, okay, step 2, we're going to put down that positive x is to the right and positive y is up. And then step 2 is done. Step 3 says look at your vectors. So our normal force vector, F stop, and then W, and then see if there's any vector that's not lined up with either the X or Y axis, you have to do SOHCAHTOA. So in this case, we don't have to do any SOHCAHTOA because all of our vectors are lined up with either the X or the Y. Step 4 is going to be sum our forces in the X and Y direction. So I'm just going to go ahead and I'm going to say sum my forces in the X, which if I look at my forces in the X direction, the only force that I see is F stop. And now F stop is going to the left. And the way I've defined my reality here, you can see I've highlighted my coordinates. I said that my reality is that positive X is to the right. So that means that this is going to be negative F stop is my force that's in the X direction. And I don't see any other forces. So I just set that equal to MAX. All right, to be even Steven here, we're going to sum our forces in the Y direction. I'm going to kind of do it right here, sum our forces in the Y. And then again, we've had this over and over again, but we have our normal force going up, minus W going down, and that's equal to MAY. But in this case, hockey pucks, it's going side to side, so it has no acceleration in the Y direction. So we know that this is just equal to 0. So that means that N is equal to W. And we know that W is equal to mg because that's the equation for weight. So I'm actually just going to circle this equation because that seems to keep coming back, that our normal force is equal to weight is equal to mg. All right, and then we come over here and put a check by step 4, complete. Step 5 says go ahead and use our physics format to solve this bad boy. So we're going to say given, want, equation. So in this problem, the numbers that they tell us, I'm going to go ahead and highlight them here. Hockey puck of mass 0.25. It's being shot to the right at a speed of this. The puck hits the board, so the stopping force is 900 newtons. It brings it to rest, and we want to know, we want to know the stopping time. So for givens here, that mass is 0.25 kg, and then it's being shot to the right, and that's its initial speed because it was cruising along at 38.1 meters per second, and then it hits the boards and comes to rest. So we know the final velocity, if it comes to rest, must be 0. And then it says stopping force, what we call f-stop, is equal to 900 newtons. And then I don't believe we know anything else. So we say, okay, what is it that we want? We want the time. So we think back on our kinematics equations. We definitely had equations that had time in there. Real quick, I'm just going to check our equation 4. Equation 4 equations don't have time. But what's going to happen here is we remember that acceleration is important because that acceleration is the link between our equations in step 4 with our kinematics ones. So I'm just going to go over here and I'm going to say my acceleration in the x direction, if I were to divide this mass over on both sides, is just going to be negative f stop over m. And I'm just going to do that because I know that it's nice to have my acceleration if we're going to use our kinematics equations. So and I'm going to circle this one here. All right, so I want an equation, if I look at my kinematics ones, that's going to have a VO, a V, and a T. And our kinematics equations never had mass and they never had force. So I'm looking for VO, I'm looking for V, I'm looking for T. And ideally there'd also be an acceleration in there because I could figure out my acceleration because I have this equation right here. So the equation that I looked back and I found right away was that V is equal to VO plus AT. And that I know I can solve that thing. So if I bring the VO over to the other side, I'm going to have V minus VO equals AT. And then I divide by A on both sides. So I actually am going to get that T is equal to V minus VO over A. And I look up here and I'm like, well, I know VO, I know V, I don't know A. But I'm going to say, oh, I actually do know A because I know A. If I said I wanted my acceleration, it says it's negative f-stop, which f-stop is 900 newtons over m, which m is 0.25 kilograms. So if you do that, you can actually get your acceleration, which is going to be negative 3,600 meters per second squared. So our step 4 equation actually was pretty helpful there because we got the acceleration. It's negative because the hockey puck's going to lose speed as it hits the boards. So I'm kind of getting run out of room here, but we're going to have 0 minus 38.1 meters per second all over negative 3,600 meters per second squared. And what's nice is you have a negative on top and the bottom, so your negatives will cancel. And that makes sense because you should never have negative time because we're not time traveling. And then when you do crunch this one, I believe you're going to end up with a really small time of 0.011 seconds. So on the, yikes, I ran out of room. I'm just going to write it right here, but your time is going to be 0.011 seconds. Will be our final answer.